Good morning, friends. Welcome for this today's lecture. We'll discuss today is the topic on in the fourth module. Next topic, that is a DC motor. Okay, we'll see today principle of operation of it. Okay, so it's a principle of operation of a DC motor can be stated that like when it should be when okay when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. This is the principle of operation of a DC motor. Okay, so meaning of this one is whenever you place north and south. Okay, so whenever you place current carrying conductor, this is your conductor which carries a current through, that means supply is given to that conductor, right? So when you are given supply to this conductor, so current carrying conductor is placed in a magnetic field. Okay, current carrying conductor which placed in a magnetic field which experiences a force. Meaning of that is experience of force is nothing but your conductor starts moving, means rotating. Okay, here it starts rotating, experiences a mechanical force, means it starts moving. Okay, that is based on this principle your DC motor is going to work. Let's see what you mean by that. Okay, that is, in DC motor, field winding produces a required magnetic field while armature conductor play a role of carrying current. Okay, current carrying conductor, and hence armature conductor experiences a force. Okay, you can observe here, so south and north poles, so here dotted lines, what dotted lines are your flux or magnetic field, and a cross mark with a cross mark circle with a cross mark is indicating your conductor. When you have supply is given to that, okay, when supply given to that, we can say that a current carrying conductor it is. Okay, when you are placed in a magnetic field, okay, that experiences a force, means meaning of that one is it starts moving. It moves means it starts rotating, that is your motor action. Okay, so let's see the animation of this. Okay, we'll see now working principle of a DC motor by animated video. Okay, so as we have seen, this is a conductor. Okay, a current carrying conductor, just it's a working principle. Whenever you keep a current carrying conductor in the magnetic field, okay, that experiences a force. Okay, just to observe what are the materials we require for the motor construction. Okay, means how it is going to operate now and all. Construction is as discussed earlier. Okay, so it consists of main part is the armature, that is nothing but your conductor. Okay, conductor has a commutator part along with that and a brushes, and then a battery is connected to that, and that is placed, means this conductor is placed in a magnetic field. Okay, so this send and magnets are going to produce a magnetic field. Okay, so as we have seen, this arrangement is as shown. Okay, so observe, as we have said, the principle of operation, whenever there is a Z, observe, when you have given a power supply for this, okay, automatically current starts flowing through this conductor, right? This is a current carrying conductor placed in a magnetic field. Okay, so this experiences a force, means it starts rotating. Okay, so this is placed in a magnetic field. Okay, right, then it starts rotating. Okay, that experiences a force. This is called a motoring action. Okay, hope you have understood that by animated video. Okay, we'll see now. So this as we have seen the motoring action of this, remember this conductor. Okay, any current carrying conductor produces its own magnetic field. Okay, I hope you remember this. Any current carrying conductor, okay, if this, for this conductor, if you give a supply for this, okay, if you give a supply for this, what happens is it starts producing its own flux. Okay, similarly, so this flux is different. Okay, this flux is different, that is north and south magnets are there and a magnetic field it is. Okay, so then conductor is also produces its own flux. Okay, because the current is means that conductor is carrying a current. So as we know, any current carrying conductor produces its own magnetic field. Okay, therefore this conductor also produces its own flux. Then what we can say is this, now we can say that we have a two fluxes present. Okay, so one is the flux produced by these permanent magnets. Okay, so one flux is produced by this permanent magnets, and another one is produced by this um, conductor. Okay, so that conductor we have shown in this direction. Let's assume that flux of this conductor, whatever it has produced, will take its direction as like this. Okay, in this direction will take, so it completes means it comes in this way. Okay, and then we'll take it's a magnetic field direction, so it is in this way. Okay, so from this north to south. Observe the fields which I have shown only 3, it is not so. Okay, there will be a field, you can assume, right? So this field is going in this way. Observe both the cases. Okay, blue color direction is in this way. Okay, and then red color means that direction is in this way. When you are considering this part, so both the fluxes are in same way. Okay, both the fluxes are in same way, so it is going to help each other, means helping, you can say. So what about here, means flux will be more. Okay, so here this, at this part, if you are considering, observe the this side direction of the flux is in this way, and direction of this flux is, means the flux of the conductor is in this way. So it is going to weakening the flux. Okay, you can say it is a weakening of the flux. So these two are like a weakening, or whatever you can say, cancellation of the flux, because both the fluxes, if those two are opposite, then they may cancel each other, right? Opposite to each other, this part, right? So this you can understand. All right, so as we know, there will be a magnetic field or electric field by this by the conductor. Armature produces two fluxes, means one is by your permanent magnet, another one is by current carrying conductor. Okay, so what we can say is the direction of the force, or you can say rotation of the motor, can be determined by Fleming's left hand rule. Okay, left hand rule. Let's see the left hand rule. Okay, take your left hand and first three fingers of a thumb, forefinger and a middle finger. Okay, so take a thumb, forefinger and a middle finger, and stretch these three fingers perpendicular to each other. Okay, and this you can, this setup you can observe, this is the magnet. So whatever red color lines are there, those are all your magnetic field, and black color is the conductor placed there, and the current carrying conductor. Okay, and then force will be exerted here. Okay, that can be said by your left hand rule. So observe in this. So suppose your forefinger represents a magnetic field. Okay, forefinger represents magnetic field, and middle finger represents your direction of a current. Then your thumb indicates the direction of the force. Okay, so the direction of a motoring action is given by this Fleming's left hand rule. Okay, now we'll move to next topic, that is back EMF in the DC motor. As we have said, we get a bit curious about this motoring action, because so a certain period, say at the beginning, when you have placed, okay, observe carefully, when you have placed a conductor, okay, when you have placed a current carrying conductor in a magnetic field, experiences a force, it starts rotating. Remember, when it start rotating, okay, so then after that, there means this is your motoring action, right? So what happens is, um, after this, there will be a generating action, that when a conductor cuts the lines of a flux, okay, this conductor starts cutting the flux, main flux, then what happens is, so that is going to produce an induced EMF. Okay, so this is an induced EMF in the rotating armature conductor according to Faraday's laws of electromagnetic induction. This induced EMF in the armature always acts in the opposite direction. Okay, this direction is given by Lenz's law. Okay, so then in the DC motor, electrical input, that is the supply voltage, is the cause for the armature current and the motoring action, and hence this induced EMF opposes the supplied voltage. Okay, this EMF tries to set up a current through armature which is in the opposite direction to that. Okay, with the supply voltage. Remember, EB, it is indicated by back EMF is indicated by EB. Okay, it is opposite to the V. Okay, as this EMF always opposes the supply voltage is V. Okay, EB means back EMF is always, means this EMF always opposes the supply voltage, so it is called as back EMF. Okay, back EMF because of its opposing nature, right? And it is denoted as EB. Okay, though it denoted as EB, but basically it gets generated by the generating action only, right? Therefore EB can be given as 5 ZNP by 60A. We have seen in generator, right? So it is since it is induced EMF, therefore it will be 5 ZNP by 60A. Okay, and then we can observe here. So this is a motor. Okay, supply given for this. As we all know that a motor, even though motor, it has its armature resistance. Okay, Ra inside that, and EB is a back EMF produced. Okay, due to generating action in the motor. That's what it is opposite to the supply, therefore it will be indicated called as back EMF, and it is indicated as EB. Okay, let's just take its equivalent circuit. So this motor can be represented as Ra plus means EB. Okay, back EMF and armature resistance. Okay, let's see the voltage of the DC motor. V will be equal to, this is equal to this plus this. So current flowing through this is IA. Therefore V is equal to EB plus IA into RA. Therefore IA from this equation can be written as V minus EB. Okay, V minus EB divided by RA. Okay, and from this equation we can say that EB also, from this equation you can take EB also is equal to V minus IA RA. Okay, so now we'll see the significance of this back EMF. Okay, so remember one thing, in this equation EB is equal to 5 ZNP by 60A. Once you have constructed, okay, once you have constructed the DC motor or machine, P remains same. Okay, right? The number of conductors also fixed, and number of parallel paths also fixed along with that, and the flux produced in the machine is also fixed. 60 is a constant term. Therefore N is only a variable part here. Okay, therefore EB will be directly proportional to N. Okay, so then how we can say this is the one observation made, and it is a very significance also we can say. The basic principle of this fact is that the back EMF is proportional to the speed. EB is proportional to N. Okay, now we'll see how loading affects on the back EMF. Okay, when you load, observe on the machine, when you load it, okay, when you load the machine, that is a motor, when you give a load on that, then what happens there is your IA start increasing. Okay, so IA start increases when a load increases, so IA start increases. When IA start increases, voltage drop of IARA also increases. Okay, when IARA start increases, though, so this difference of V minus IARA is goes on decreases. Meaning of this one is VEB is decreases. Okay, as we know this, that key EB is directly proportional to N. When EB decreases, okay, similarly means as your EB decreases, your speed of the machine is also start decreasing. Okay, therefore, so back EMF regulates the flow of armature current. Okay, it regulates the flow of armature current and it automatically alters the armature current to meet the load requirement. This is the practical significance of the back EMF. Okay, and remember at the beginning, okay, at the beginning, okay, so at the beginning, speed of the motor will be equal to 0. Therefore EB is also equal to 0. Okay. Next, we'll move to the torque equation of a DC motor. Okay. So consider what you mean by a torque. Torque is nothing but the turning or twisting force. Okay. About an its axis is called as a torque. Okay. It's a twisting force, we can say, right? To derive a torque equation of a DC motor, we'll consider a wheel of a radius r. Okay. R meters acted upon by the circumferential force F newtons. Okay, as shown here. Right, this is your consider a wheel. Okay, with a radius r, with in this direction rotation, and this is the exerted force. Okay, so the wheel is rotating at a speed of n rpm. Okay, so then what we can say is angular speed can be given as omega is equal to 2 pi n by 60 radian per second, as we know, right? Then we'll calculate what is the work done in one revolution. What is the work done in one revolution? What is the work done in one revolution? That is W is equal to force into distance traveled. Okay, that we have considered as one revolution. Therefore F into distance traveled in one revolution. Therefore F into, so distance traveled in a circle is what? Circumference of the circle. It is nothing but 2 pi r. So radius is r, so F into 2 pi r joules. Okay, this is the work done. Now we'll see what is the power developed in one revolution. That can be given as P is equal to, as we know, P is equal to work done per unit time. Okay, so per second also you can say. So work done by time for one revolution. So work done we have already calculated. It is F into 2 pi r divided by time is 60 by n. Therefore Fr you keep aside and you can take this just to simplify. So here you get 2 pi n by 60. So as we know, 2 pi n by 60 is nothing but your omega. Substitute Fr you can keep as it is. So as we know, torque is the twisting force, so we can represent, let's take P is equal to, this can be represented as T into omega watts. Here torque, this T is the torque in Newton meter. Okay, omega is the angular speed in radian per second. Let's take TA is the armature torque. Then what we can do is P is equal to TA into W. Okay, that is omega. P is equal to TA into omega. So what is the P? Power developed by the motor is nothing but back EMF into current flowing through that. That is IA. Okay. Therefore, EB into IA will be equal to TA. Okay, as it is, and omega is 2 pi n by 60. Therefore, what you know, what is the formula for EB? EB is equal to 5ZNP by 60A. Substitute in this equation. Okay, and then let's see in this equation, n is a common term, 60 is a common term. So what we require, TA we require just to get to TA is equal to what? Just 2 pi, send this side, it will be 1 by 2 pi. Okay, and remaining these all terms, that is 5 Z P by A into I. Okay, that can be written in this form. Okay, 5ZP by A into IA. So just to rearrange, and 1 by 2 pi is nothing but 0.159 pi IA P Z divided by A. So torque in armature torque, or torque equation of a DC motor in Newton meters. Okay, hope you have got this. Remember, for exams they'll be asking you what is the torque equation. Okay, torque equation for a DC motor. You're supposed to draw this derivation. Okay, thank you.